A linear transformation is a rule that moves vectors while keeping lines straight in the origin. Fixed. It must satisfy two properties: additivity and homogeneity. Before we talk about rank, we must understand the kernel. The kernel is the null space, the set of all input vectors that are crushed to zero. Consider this matrix. The second row is all zeros. If we take the vector -2, 1, the transformation multiplies it to become 0. This vector dies. It enters the kernel. The rank nullity theorem is a conservation law for dimensions. Think of the input dimension as a fixed amount of energy. When a linear transformation acts on a space, it splits that dimension into two parts: the rank, which is the dimension that survives, and the nullity, the dimension that is crushed to zero. In linear algebra, a transformation maps vectors from one space to another. The kernel is the null zone, the collection of all vectors that land exactly on zero. Let's start in 1D. Imagine a number line. If our transformation is multiply by 0, every single point on the line collapses into the origin. Here, the entire 1D space is the kernel because everything was flattened to 0. Consider a transformation that projects everything onto the x-axis. The vertical axis collapses to 0. This line is the kernel, so the nullity is 1. The horizontal axis survives. This is the image, so the rank is 1. Let's look at a 2D numerical example. Consider this matrix where the second row is exactly twice the first. This means the rows are linearly dependent. If we multiply the matrix by the vector -2, 1, we get the 0 vector. This vector lives in the kernel. In this transformation, the entire 2D plane collapses into a 1D line. One dimension is preserved as rank, and one dimension is lost to the kernel. Now let's enter 3D space, where our total dimension is 3. We'll use sliders to change the matrix values and see the rank collapse. First, we set the bottom row to 0. Numerically, any vector with only a z component will land at 0. The 3D volume collapses into a 2D plane. What if we make the first two rows identical? Now, they are linearly dependent. The 2D plane collapses further into a 1D line. Finally, if the matrix is all zeros, the rank is 0. The entire 3D space is the kernel, and everything lands at a single point. No matter how you squash the space, the sum of what remains and what vanishes will always equal your starting dimension.